We do not have a single rock from the first 600 million years of Earth. Not one. Every stone from that time has been destroyed, melted many times over in the long subduction cycle of a young planet with an active convecting mantle, shattered countless times by the steady meteor bombardment of the early solar system, eroded, weathered, metamorphosed, or dragged back down into the deep interior, remelted and returned to the surface in some later form that no longer carries any signature of what it once was. From the eon we call the Hadean, 4.56 billion years ago, down to roughly 4 billion years ago, the first and longest era of the planet's existence, we have almost nothing. The oldest intact rocks on the surface of Earth are about 4 billion years old. The Acosta gneiss in the Canadian Shield, rocks from southwestern Greenland, fragments from northwestern Australia. These are, already, Archean rocks, from the beginning of the eon that followed the Hadean. They are among the oldest things any human has ever held, but they are not Hadean. They miss the Hadean by at least 50 million years. What we know about the first 600 million years of Earth we have inferred from meteorites that preserve the chemistry of the original solar nebula from which Earth and all the other planets formed, inferred from the heavily cratered surface of the Moon, which still carries the scars of bombardments that Earth experienced at the same time, inferred from a handful of tiny mineral grains, crystals of a remarkably durable silicate called zircon, smaller than grains of rice, preserved by improbable luck in certain very ancient sedimentary deposits, inferred from models of how planets assemble, from the physics of magma oceans, from the chemistry of gas escape, from the orbital dynamics of a young moon retreating slowly from a younger planet. The Hadean is, in an unusually direct sense, a reconstructed eon. The work of knowing it is the work of detective reading, piecing together what the surviving fragments can tell us and what they cannot. Some of it we are confident about. Some of it we are still arguing over. Much of it we will probably never resolve. This is the story of that reconstruction, of what happened on Earth during those first 600 million years, to the best of what we now know. Before there was an Earth, there was a disk of gas and dust. 4.567 billion years ago, in a region of the Milky Way galaxy that did not yet contain a solar system, a large cloud of interstellar material, roughly 50 astronomical units across, composed mostly of molecular hydrogen and helium with small quantities of heavier elements, began, for reasons we still only partly understand, to contract. The contraction may have been triggered by the shock wave of a nearby supernova explosion, whose expanding debris compressed the local region of interstellar medium until gravity took over. Or it may have been triggered by a chance density fluctuation within an already gravitationally marginal cloud. In either case, once the collapse began, it did not stop. As the cloud contracted, most of its mass flowed inward toward the center, where pressure and temperature rose to the point at which hydrogen fusion could sustain itself. A star ignited. It was not yet our sun in any form recognizable to us. It was a young protostar, still wrapped in clouds of infalling material, still growing, still radiating much of its energy in the infrared. But it had begun. And around it, in a flattened disk of dust and gas conserved from the original collapse, material that had not fallen into the star settled into orbit. The disk was called, by astronomers who have since identified many similar structures around young stars elsewhere in the galaxy, a protoplanetary disk. It extended, in the case of our solar system, from just outside the forming sun out to perhaps 50 or 100 astronomical units. Closer to the star, temperatures were high enough that only refractory materials, metals and silicates, could condense into solid particles. Further out, where temperatures were lower, volatile compounds like water ice, ammonia ice, and methane ice could also freeze into solid form. The boundary between these two regimes is called, in planetary science, the snow line, and its position determined to a first approximation what kind of planet could form at each distance from the Sun. Inside the disk, the dust particles that had condensed from the cooling gas began to collide, to stick together, to grow. Electrostatic forces, the static cling you feel when you pull a sweater off your head in winter, held the smallest grains together. As the particles grew larger, gravity became increasingly important. By 100,000 years or so after the disk formed, the dust grains had accumulated into bodies ranging from millimeters to perhaps kilometers in size. These are called planetesimals. They're the building blocks out of which planets form. In the inner disk, where only metals and silicates could survive the temperatures, planetesimals composed almost entirely of rock and iron accumulated. In the outer disk, beyond the snow line, planetesimals composed of rock, iron, and large fractions of ice formed. The gas giants of the outer solar system, Jupiter, Saturn, Uranus, Neptune, grew from these ice-enriched planetesimals, eventually accumulating enormous atmospheres of hydrogen and helium, directly from the remaining nebular gas before the young sun's intensifying radiation swept the gas away. The rocky inner planets, Mercury, Venus, Earth, Mars, grew more slowly. They did not have access to nebular gas in the same way. They had to be built from collisions between smaller rocky bodies. The process was slow and inefficient. It would take, in Earth's case, something like 100 million years to assemble a body of approximately its final mass. And during those 100 million years, the young planet would go through everything that we now call the Hadean. The accretion of Earth was not a gentle process. Planetesimals in the inner solar system were moving in roughly circular orbits with speeds of around 30 kilometers per second, the orbital velocity of anything in Earth's vicinity around the young sun. When two planetesimals collided, the collision was high energy. The kinetic energy of the impacting body, most of it converted to heat on impact, was more than enough to partially or completely melt both bodies. Early in the accretion process, when the bodies involved were small, much of this heat radiated back into space. Later, as the growing Earth became a significant body of its own, the heat from each incoming impact was retained. By the time the proto-Earth had reached perhaps half its final mass, the combined effect of accretion heating, the decay of short-lived radioactive isotopes, particularly aluminium-26 and iron-60, which were still abundant in the early solar system, and the gravitational potential energy released by the sinking of iron-rich material toward the center, had made the interior of the young planet entirely molten. The proto-Earth was, at that stage, essentially a large ball of molten rock and metal, with a thin, temporarily solid crust that was constantly being disrupted by continuing impacts. One of the most important consequences of this molten state was differentiation. In a fully molten body, heavier materials sink and lighter materials rise. Iron and nickel, which were abundant in the accreting planetesimals, were denser than the surrounding silicate rock. They sank across tens of millions of years toward the center of the proto-Earth, accumulating there as an iron-nickel core. The silicate material, lighter, remained above, forming what would eventually become the mantle. This differentiation is one of the best dated events in early Earth history, because the relative abundances of tungsten isotopes, specifically the ratio of tungsten 182 to tungsten 184, which depends on whether hafnium 182, with a half-life of 9 million years, decayed before or after the iron separated from the silicate, provide a sensitive clock for when differentiation happened. The measurements place the main phase of Earth's core formation at approximately 4.53 to 4.51 billion years ago, roughly 50 million years after the beginning of the solar system. The separation of the core was itself an enormous energy event. As iron-rich material sank toward the center, it released gravitational potential energy. This energy went into heat, enough heat, in fact, to significantly raise the temperature of the proto-Earth beyond what the accretion alone had produced. The young planet, immediately after core formation, was in its most molten state of its entire existence, a true magma ocean, possibly extending down through most of the mantle, surrounded by a thin atmosphere of outgassed volatiles and still being struck, though increasingly rarely, by incoming planetesimals. And then, somewhere in this early phase of Earth's history, one of those incoming bodies was extraordinarily large. The body is called Theia. The name comes from Greek mythology. Theia was the mother of Selene, the goddess of the moon. The name is appropriate because Theia, in our current understanding of early solar system history, is the object whose collision with the proto-Earth produced the moon. Theia, as the hypothesis requires, was roughly Mars-sized, about half the diameter and 1/10 the mass of the proto-Earth. It formed somewhere in the inner solar system in an orbit close enough to Earth's that the two bodies would eventually cross paths. The current best reconstruction of its origin suggests it formed at one of the two Lagrangian points, the stable orbital positions 60 degrees ahead of or behind Earth in its orbit around the Sun, where a smaller body can coexist with a larger planetary neighbor. From that relatively stable position, gravitational perturbations from other forming planets, particularly Jupiter's gravitational influence reaching down into the inner solar system, gradually destabilized Theia's orbit. Eventually, it crossed Earth's path. The collision happened at approximately 4.51 billion years ago, roughly 60 million years after the start of the solar system. It was, by planetary standards, a glancing blow. Theia did not strike Earth head-on. Current simulations suggest the impact angle was something like 45 degrees, with Theia approaching from one side and hitting the Earth at a speed of perhaps 12 to 15 kilometers per second. The collision vaporized the outer layers of both bodies. A superheated cloud of rock vapor, molten droplets, and ejected debris spread outward from the impact site, forming a temporary disk around the partially destroyed Earth. Within this disk, material that was close enough to Earth fell back down to the surface, adding its mass to what was left of the Earth after the impact. Material that was far enough out remained in orbit. The two bodies had, in the hours of the impact itself, become one, and then, as the debris settled into orbit, began to separate again. The orbital disk condensed within perhaps 1,000 years into one or more moons. If there were multiple early moons, most of them quickly merged. Within 10,000 years of the impact, a single moon orbited Earth, containing most of the material that had remained in orbit and much of what had originally been Theia. The consequences of the impact for Earth itself were dramatic. The surface was remelted globally. The atmosphere, such as it was largely blown off. Whatever early crust had managed to form was obliterated. The Earth, after the impact, was starting over, a fully molten body spinning rapidly from the angular momentum imparted by the collision, with a bright, hot moon disk overhead whose light could not yet be separated from the glow of the molten surface below. Evidence for the impact and for the identity of Theia as an independent body comes from several converging lines of analysis. The moon's bulk composition is similar to Earth's mantle but depleted in iron, consistent with the idea that the moon formed from the silicate portions of both Earth and Theia, with most of the iron of both bodies having already sunk to their respective cores before the impact. The angular momentum of the Earth-Moon system is consistent with a high-velocity glancing impact. The remarkable isotopic similarity between Earth and the Moon, their oxygen isotope ratios are indistinguishable to within measurement precision, is explained if the impact thoroughly mixed the silicate material of Earth and Theia during the vaporization phase. And the geology of both bodies, worked out over the past 50 years of lunar sample analysis and terrestrial deep-time research, fits the picture of a single catastrophic event early in solar system history from which both the Earth and its moon were born together in their current shared form. In the immediate aftermath of the Theia impact, Earth was a world of molten rock. The surface temperature, averaged across the planet, was probably somewhere between 2,000 and 3,000 degrees Celsius. The entire outer layer of the planet, perhaps down to a depth of hundreds or even thousands of kilometers, was liquid. A true magma ocean, continuous, global, seething with convection currents that carried heat from the interior to the surface where it could radiate away into space. The surface of this magma ocean would not have been still. Convection, driven by the enormous temperature difference between the top and bottom of the molten layer, kept the surface in constant motion. Slow waves hundreds of kilometers across rolled across the surface of the ocean. Plumes of hotter material rose from below and spread outward at the top. Cooler, slightly denser material sank back down toward the interior. The process was continuous. The heat flow out of the young Earth at this stage was perhaps 100 times what it is today. A thin skin of cooler material may have formed at the top of the magma ocean in the form of a floating crust, but this crust was unstable. Continued meteor bombardment, convection currents rising from below, and the sheer rate of heat escape meant that any crust that formed was quickly disrupted, partially remelted, and reformed again elsewhere. The young Earth was, in a real sense, in constant resurfacing mode. The crust of one afternoon, on a long enough time scale, would not be the crust of the next afternoon. Above this molten surface, the atmosphere was doing its own thing. The impact had largely stripped the Earth of its original primary atmosphere, the hydrogen and helium it had accreted directly from the solar nebula. That primary atmosphere, which had been held only weakly by Earth's gravity, had in any case largely escaped to space before the impact. What took its place immediately after was an atmosphere of vaporized rock. For perhaps 1,000 years after the impact, as the magma ocean radiated away its enormous excess heat, Earth's atmosphere was, literally, rock vapor. Vaporized silicates, magnesium oxide, iron oxide, gaseous at the temperatures of the fresh magma surface. This atmosphere was opaque to outgoing thermal radiation, acting as a kind of enormous greenhouse that kept the surface hot and the atmosphere itself even hotter. Eventually, as heat radiated through the top of the atmosphere, the temperature at the outer edge dropped below the condensation point of the various rock-forming compounds. Liquid silicate droplets rained out of the upper atmosphere, falling back down onto the still molten surface. Across perhaps 1,000 years, the rock vapor atmosphere condensed out entirely. What was left was a much thinner atmosphere of harder-to-condense gases, and it was in this secondary atmosphere that the chemistry of Earth really began. What the young Earth outgassed from its mantle into the atmosphere was whatever volatile compounds had been trapped in the accreting material. The accretion of Earth had included, mixed in with the silicate and iron building blocks, a small fraction of volatile-rich material: water, carbon dioxide, carbon monoxide, methane, nitrogen, sulfur compounds, hydrochloric acid, and various other small molecules had been present in modest abundance in the planetesimals that built the planet. During the Magma Ocean phase, these volatiles, unable to remain dissolved in the molten silicate at surface pressures, exsolved, bubbled out of the magma, and entered the atmosphere above. The composition of this secondary atmosphere was, as best we can reconstruct it, dominated by carbon dioxide and water vapor, with significant nitrogen, smaller amounts of sulfur dioxide and hydrogen chloride, and trace quantities of methane, ammonia, and hydrogen. Exactly how much of each was present depends on assumptions about the oxidation state of the young mantle, which is still debated. Some models favor a more reducing atmosphere with more methane and hydrogen. Others favor a more oxidizing atmosphere with almost all carbon in the form of CO2 and very little methane. The truth is probably somewhere between, and it may have changed substantially over the hundreds of millions of years of the Hadean. The pressure of this secondary atmosphere was, in the early phases, probably enormous. Surface pressures of 100 atmospheres or more have been proposed, 100 times the modern atmospheric pressure. Most of this was carbon dioxide, outgassed in large quantities from a very hot early mantle. The atmospheric pressure would drop across the Hadean, however, as carbon dioxide was gradually absorbed into the oceans and ultimately into carbonate rocks on the sea floor. By the end of the Hadean, atmospheric pressure may have been closer to the values we know today, although the composition was still very different. What was missing from this secondary atmosphere entirely was free oxygen. Oxygen is not something you outgas from a reducing mantle. Oxygen on Earth came later, a product of biological activity, specifically of oxygenic photosynthesis, which would not appear for another 2 billion years. The Hadean atmosphere, and indeed the atmospheres of the entire Archean eon that would follow, were essentially anoxic. If you had breathed the air of the Hadean Earth, you would have suffocated. If you had breathed the air of the Archean Earth, you would have suffocated. Free oxygen, the gas your body needs, is a late arrival on this planet. For most of Earth's history, the air contained almost none of it. What that air did contain, crucially, was water vapor. And water vapor, once the surface cooled enough, could condense. The formation of Earth's oceans is one of the key transitions of the Hadean. It required first that the surface cool below the boiling point of water at whatever the surface pressure was. At 100 atmospheres of pressure, Earth's very earliest atmosphere, water boils at about 300 degrees Celsius. As the pressure dropped and the surface cooled, this threshold became easier to cross. Once the surface was below the boiling point, water vapor condensed out of the atmosphere as rain and liquid water accumulated on the surface. The first rain on early Earth may have fallen for a very long time. If the atmosphere initially contained an equivalent of several oceans' worth of water vapor, and if the surface cooling was relatively fast, the condensation may have happened in a geological blink. Tens of thousands of years of near-continuous rainfall pouring out of a thick, dark atmosphere onto a newly solidified basaltic crust, filling low-lying basins and forming for the first time the Earth's oceans. The timing of ocean formation is still somewhat uncertain, but several lines of evidence suggest it happened earlier than was once thought. The cool. Early Earth hypothesis, which we will come to shortly, proposes that by 4.4 billion years ago, essentially at the beginning of the Hadean proper, after the immediate recovery from the moon-forming impact, Earth's surface had already cooled enough to support large bodies of liquid water. The evidence comes primarily from the Jack Hill's zircons, whose oxygen isotope signatures suggest crystallization from magma that had interacted with liquid water at the surface. If the zircons are correctly interpreted, then Earth had oceans for essentially the entire Hadean, 600 million years of liquid water under a thick CO2 atmosphere, above a mantle still much hotter than today. Where did the water come from? The answer, as best as we currently understand it, is that it came from two places. Some of the water was present in Earth from its original accretion. Volatile rich planetesimals, particularly those that formed further out in the protoplanetary disk where temperatures were cooler, delivered water along with their other constituents. Some of the water, though probably a smaller amount, arrived later, in comets and carbonaceous asteroids that continued to strike Earth through the Hadean and into the Archean. The relative importance of these two sources has been debated for decades. One of the clearest lines of evidence comes from the isotopic composition of terrestrial water. Water molecules, depending on where they formed in the solar system, have slightly different ratios of the hydrogen isotopes, hydrogen-1 and deuterium. Comets, which formed in the cold outer solar system, tend to have relatively high deuterium to hydrogen ratios. Carbonaceous chondrite meteorites, which formed further in, tend to have ratios closer to Earth's. Modern ocean water, when measured, has a D/H ratio that matches carbonaceous chondrites well and that matches most comets poorly. The implication is that most of Earth's water came from the outer asteroid belt, delivered by bodies that formed not too far beyond the snowline, but were scattered inward during the early solar system's dynamical instabilities. The amount of water on Earth, compared to what we would naively expect given its formation zone, is in fact one of the most striking features of the planet. Earth has significantly more water than most models of inner solar system planetesimal composition would predict. The excess is explained in current thinking by relatively efficient delivery from further out during the turbulent early phases of the solar system, including possibly large water-rich bodies that happen to cross Earth's orbit and contribute a significant fraction of their water upon collision. Regardless of the exact pathway, the result is clear. By the middle of the Hadean, Earth had an ocean. Possibly several oceans worth of water, in fact, because the surface area for liquid water was larger at lower atmospheric pressure, and because some fraction of the water may have been trapped in the upper mantle rather than on the surface. The young planet was, in its early Hadean phase, already a water world. The oldest things on Earth you can hold in your hand are tiny crystals of a silicate mineral called zircon. They come from a ridge in Western Australia in a place called Jack Hills in the narrower gneiss terrain of the Yilgarn Craton. The rocks of the ridge itself, metamorphic gneisses, are only about 3 billion years old, but embedded within some of those rocks as trace detrital grains are zircons that are older, some of them considerably older. Zircon is a hard, chemically resistant mineral composed of zirconium silicate with the chemical formula ZrSiO4. It has the remarkable property that, when it crystallizes from a magma, it incorporates uranium into its crystal lattice, but strongly rejects lead. This means that when a zircon first forms, it contains some quantity of uranium and essentially no lead. As time passes, the uranium decays into lead at a precisely known rate, uranium-238 to lead-206, uranium-235 to lead-207. By measuring the ratio of lead to uranium in a zircon today, and knowing the decay rates, you can calculate to impressive precision when the zircon originally crystallized. The uranium-lead method on zircon is one of the most reliable dating techniques in all of geology. It can routinely date zircons to within about 1 million years. The oldest Jack Hill zircon that has been successfully dated is 4,404,000,000 years old, give or take 8 million years. It was dated in 2001 by a team led by Simon Wild, including John Valley, William Peck, and Colin Graham. The analysis was done on a single crystal only about 1/10 of a millimeter across, roughly the size of a grain of table salt. But its uranium-lead ratio, read out by careful ion microprobe mass spectrometry, placed its origin at more than 4.4 billion years ago, older than any other crystal ever found on Earth. The Jack Hill zircon, at 4.4 billion years, is only about 160 million years younger than the moon-forming impact. It formed during what was supposed to be, in the older view of the Hadean, a still essentially molten or semi-molten Earth. And what the zircon tells us, when we look at it more carefully, contradicts that older view. The zircon contains, in addition to the uranium and lead that we use to date it, small amounts of oxygen, specifically oxygen isotopes in the ratio of oxygen-18 to oxygen-16. The ratio of these two isotopes, locked into the zircon crystal when it first formed, reveals something about the magma from which it crystallized. The oxygen isotope ratio tells us whether that magma had previously interacted with liquid water at the surface or not. Magma that has been in contact with liquid water at low temperatures, the kind of contact that happens when oceanic crust is altered by circulating seawater at a mid-ocean ridge, or when sedimentary rocks containing water-altered minerals are melted, carries a distinctive elevated oxygen-18 signature. Magma that has never been near liquid water, that has come directly from the deep mantle without surface alteration, carries a different signature with less oxygen-18. The Jack Hill zircons carry the elevated signature. They crystallized from magma that had, somewhere in its prior history, interacted with liquid water at a low temperature, which means 4.4 billion years ago there was already liquid water on Earth. Since the 2001 paper, many hundreds more Hadean zircons have been dated and analyzed from the Jack Hills deposit and from other similar places. The picture has become increasingly detailed. There were not just a few zircons from before 4.3 billion years ago. There were many, perhaps many thousands, embedded as detrital grains in younger rocks that preserved them while the original rocks they came from were destroyed. The chemistry of these zircons, read out across hundreds of individual grains, consistently suggests that the early Hadean crust was at least partially granitic, the kind of lighter, silica-rich rock that forms on modern Earth in continental settings. The Hadean Earth, it seems, may have had something at least resembling the distinction between oceanic and continental crust, even at 4.4 billion years ago. This was not what the older textbooks taught. The picture of the Hadean that prevailed through most of the 20th century was of a world that could barely be called a planet yet. The standard textbook description into the 1990s was roughly this. The Hadean was a hellish period. The name Hadean itself comes from Hades, the Greek underworld, characterized by a surface that remained molten or near molten for most of the eon, an atmosphere so hot that no liquid water could exist, constant meteorite bombardment, and no possibility of any environment that could have supported life. The first stable crust, The first liquid oceans, the first conditions under which early life might have emerged, were all placed at the very end of the Hadean, right around the transition to the Archean, roughly 4 billion years ago. Everything before that was, in the older view, too hot and too chaotic to support a recognizable planetary surface at all. The Jack Hill Zircons and the research that has followed from their discovery and analysis have largely overthrown this picture. In 2002, John Valley, William Peck, and Elizabeth King, the same research group that had dated the oldest Jack Hill zircon, published a paper titled A Cool Early Earth. In it, they argued, on the basis of the oxygen isotope evidence from the zircons, that Earth's surface had been cool enough for liquid water for essentially the entire Hadean. Not just at the very end, not just for brief intervals, but continuously, from about 4.4 billion years ago onward, the conditions for liquid water had been met. The Hadean, they proposed, was not a continuous hell. It was, for most of its duration, a planet with oceans, a planet whose surface was, in many respects, more like the modern Earth than like the fiery vision of older textbooks. The subsequent 20 years of research have, by and large, confirmed this view. The zircon record is consistent with a relatively quickly cooled post-Theia Earth. The modeling of magma ocean solidification suggests that most of the magma ocean crystallized within a few million years of the Theia impact, with the final remnants disappearing within a few tens of millions of years. By 4.4 or 4.3 billion years ago, the surface was certainly solid and probably wet. The continuing impact bombardment was, by that time, intense but not continuous. Individual impacts could locally vaporize oceans, but between impacts, the ocean chemistry and surface conditions could recover. This recalibration of the Hadean matters enormously for the question of when life appeared on Earth. If liquid water was available from 4.4 billion years ago onward, and if the surface had stable environments, however locally disrupted by impacts, for most of the Hadean, then the window of time during which pre-biotic chemistry could have operated, and during which life could have emerged, is much longer than the older picture suggested. Instead of 100 or 200 million years of possible pre-biotic chemistry before the end of the Hadean, we now have something like 400 million years. This is a substantial difference. It means, among other things, that the origin of life does not require unusually fast pre-biotic chemistry. It could have taken a long time, in environments that were available for a long time. The Hadean, in the modern view, was not a barren hell. It was a young planet, still actively cooling, still being bombarded, still chemically unsettled, but with oceans, with an atmosphere, with conditions that may have been, for much of the eon, surprisingly amenable to the kinds of processes that lead eventually to life. But the Hadean had a climate problem that the modern Earth does not. The sun, when it was young, was significantly dimmer than it is today. This is not a matter of guesswork. It is a well-understood consequence of stellar evolution. Stars, as they age on the main sequence, gradually increase in brightness because the fusion reactions in their cores become slightly more efficient as the helium fraction increases. Our sun, 4.5 billion years ago, was emitting something like 70% of its current luminosity. This should have been a serious problem for the young Earth. If you take the modern Earth's atmospheric composition and place it under a sun that is 30% dimmer, the resulting climate is deeply cold. Calculations suggest the surface temperature would fall well below the freezing point of water, and the entire planet would glaciate. A full planet snowball Earth, locked in ice across the entire surface. Yet all the evidence we have from the Hadean and early Archean, the Zircons, the earliest sedimentary rocks of the Archean, the apparent existence of liquid water, the evidence of early biological activity suggests that Earth was not frozen in the Hadean or the early Archean. The surface, as best we can tell, had liquid water and temperatures in the range that could support biochemistry. Somehow, the Earth kept itself warm under a significantly fainter sun. This is the faint young sun paradox. It has been recognized since the 1970s when Carl Sagan and George Mullen first worked out the magnitude of the stellar luminosity difference and realized the apparent contradiction with the geological record. The resolution, most geochemists now agree, lies in the atmospheric composition of the young Earth, an atmosphere significantly richer in greenhouse gases than today's atmosphere would have trapped enough extra infrared radiation to compensate for the dimmer sun. Carbon dioxide, outgassed from the mantle in very large quantities during the Hadean, was certainly one contributor. The early atmosphere may have held at some stages hundreds to thousands of times as much CO2 as the modern atmosphere, producing a correspondingly strong greenhouse effect. But CO2 alone may not have been enough. More recent work has emphasized the possible role of methane, which is a much stronger greenhouse gas per molecule. Methane, in an anoxic atmosphere, is relatively stable and can persist in significant concentrations. Once microbial methanogens evolved, probably early in the Archean, they would have added methane to the atmosphere, further reinforcing the greenhouse. Other possibilities include nitrogen-hydrogen collision-induced absorption, a subtle atmospheric chemistry effect that can add substantial warming if the atmosphere contains significant molecular hydrogen, and higher atmospheric pressure in general, which broadens the absorption bands of any greenhouse gas and makes it more effective. The specific balance of these contributions is still being worked out. What is certain is that the young Earth had an atmospheric composition that was, in whatever specific combination, significantly better at greenhouse warming than our modern atmosphere. The consequence was that even with a dimmer sun, the planet stayed warm enough for liquid water. And as the sun slowly brightened over geological time, the composition of the atmosphere slowly shifted, maintaining through a set of feedback loops that we are only now beginning to understand in detail, a temperature range that could support liquid water and the biochemistry it enables. The faint young sun paradox is not, in modern geochemistry, really a paradox anymore. It is an observation that the young Earth's atmosphere was different from the modern Earth's atmosphere in ways we can, roughly, constrain. But it is also a reminder that Earth's climate has been kept within habitable bounds across 4 billion years of massive changes in solar output and atmospheric chemistry by a set of self-stabilizing feedback processes that we still do not entirely understand. Through the entire Hadean and well into the Archean, Earth was being struck by large objects. The Moon preserves the record of this bombardment with unusual clarity. Lunar craters, because the Moon has no atmosphere, no weather, and essentially no active geology, remain essentially undisturbed for the entire age of the solar system. Every major impact in the Moon's history is still visible as a preserved feature, from the great mare basins of the near side, Imbrium, Serenitatis, Tranquillitatis, Crisium, down through smaller craters to the finest microcraters on individual lunar rocks. By mapping and dating these craters, lunar scientists can reconstruct the bombardment history of the Moon, and because Earth and the Moon have shared the same region of space throughout their existence, they have experienced the same bombardment, though Earth, with its larger size and stronger gravity, has received proportionally more impacts, and with its active geology, preserves far fewer of them. For many decades, the interpretation of lunar impact ages pointed to a specific phenomenon called the late heavy bombardment. The idea, based on Apollo-era sample dating, was that moon-forming impacts had tapered off relatively quickly after the main accretion, but that around 3.9 billion years ago, some 600 million years after the Theia impact, there had been a dramatic spike in impact rates. A brief, intense episode of bombardment, much more severe than anything before or after, that had resurfaced much of the moon and struck Earth with a correspondingly devastating flux of impactors. The late heavy bombardment on this view was the final great insult to the young Earth, a pulse of cosmic violence that closed the Hadean and delayed the development of stable surface conditions. Recent work has substantially complicated this picture. The problem is that the Apollo samples, which provided the primary evidence for the late heavy bombardment spike, were not taken from a representative set of lunar sites. Most of them were taken from within the Imbrium basin or from sites heavily contaminated by ejecta from Imbrium. If most of the samples are, in effect, measuring the age of a single very large impact event, the Imbrium impact itself, they will cluster around that age and look like a spike in the bombardment record when they actually represent a single event and its fallout. A 2016 analysis by Patrick Bojanki and Mark Harrison, re-examining the Apollo sample ages in this light, argued that the apparent late heavy bombardment spike is a sampling artifact, and that the real history of lunar bombardment was a continuous, gradually declining tail of impacts from the heavy early bombardment of the solar system. This revised view is not yet a consensus. There is still vigorous debate, with some researchers continuing to favor a discrete late heavy bombardment episode and others agreeing with the continuous decline interpretation. But it has changed the texture of our thinking about the Hadean. The old narrative of a final catastrophic pulse at the end of the Hadean, closing the era of chaos and opening the era of stable Archean life, is less certain than it was 20 years ago. What is more likely is that the bombardment declined steadily from very high levels in the early Hadean, reached moderate levels in the middle Hadean, and continued at gradually lowering rates through the Archean and beyond, with occasional large individual impacts that could, locally, vaporize oceans and reset regional conditions, but without a single sharp cutoff event. The total flux of impactors during the Hadean, under the revised picture, is still extraordinary by modern standards. Earth received something like 10 to the 23rd kilograms of impactor mass during the Hadean, 10,000 times the combined mass of all modern asteroids. Most of this was delivered in the earliest part of the Hadean, immediately after Theia, when the leftover planetesimals of the inner solar system were still being swept up by the growing terrestrial planets. By the middle and late Hadean, the impact rate was much lower, though still dramatic by modern standards. Earth was, in other words, in a much more chaotic neighborhood than the modern solar system. And through all of this, on the cooler, wetter parts of the planetary surface, chemistry was doing something new. The molecules of life, amino acids, nucleotides, lipids, sugars, are organic compounds. They contain carbon, hydrogen, nitrogen, oxygen, and sometimes phosphorus or sulfur, arranged into specific skeletal structures. Before there was life on Earth, these molecules, if they existed at all, had to be produced by abiotic chemistry. Atoms had to combine into molecules, and molecules had to combine into more complex structures without any of the enzyme-driven machinery that modern life uses. The question of how this happened, how pre-biotic chemistry crossed the gap from simple atmospheric and oceanic molecules to the complex precursors of life, has been one of the enduring puzzles of origin of life research. The first major experimental investigation was performed in 1953 by Stanley Miller, a graduate student working with Harold Urey at the University of Chicago. Miller set up a sealed glass apparatus containing water, methane, ammonia, and hydrogen, his best guess at the time for the composition of the early Earth atmosphere, and ran electrical sparks through the gas mixture for a week, simulating lightning. At the end of the week, when he analyzed the water that had collected in the bottom of the apparatus, he found a range of organic compounds, including several amino acids, the basic building blocks of proteins. The experiment demonstrated, for the first time, that the simple molecules of an early planetary atmosphere could spontaneously produce biologically relevant, complex molecules under plausible natural conditions. The Miller-Urey experiment was and remains one of the iconic demonstrations of pre-biotic chemistry. It is not a complete theory of life's origin. The amino acids it produces are mixed, racemic, and would require further selection and concentration to build anything resembling a modern protein. But it established the basic principle that the chemistry is possible, that ordinary physical processes on a young planet can produce some of the raw material that life requires. Subsequent research has complicated the picture in various ways. The atmospheric composition Miller assumed, rich in methane, ammonia, and hydrogen, turned out to be somewhat more reducing than the composition now thought to have dominated Earth's actual early atmosphere, which was probably richer in CO2 and poorer in methane. Under a less reducing atmosphere, the Miller-Urey chemistry produces fewer amino acids, although it still produces them. Other sources of pre-biotic chemistry have been identified that do not depend on an intensely reducing atmosphere at all. Among the most important of these are hydrothermal vents. At mid-ocean ridges and at other locations where hot water emerges from the sea floor, the chemistry is quite different from the chemistry of the sunlit surface water. Hot alkaline fluids rich in hydrogen, methane, and various sulfur compounds mix with cooler seawater. The mixing zone supports a range of chemical reactions that can produce organic molecules directly. White smokers, a type of hydrothermal vent that produces alkaline rather than acidic fluids, and that is typified today by sites like the Lost City hydrothermal field in the mid-Atlantic, had been proposed by Michael Russell and William Martin, among others, as the most plausible site of life's origin on Earth. The fine, porous mineral structures of the vents, built of crystalline carbonates and sulfides, provide scaffolds where prebiotic molecules can concentrate, react, and begin to organize. The natural chemical gradients between alkaline vent fluid and acidic Hadean seawater, a gradient in proton concentration that ordinary modern cells still use, converted into chemical currency, provide free energy that prebiotic chemistry can draw on. Other hypotheses emphasize different environments. Warm little ponds, suggested by Charles Darwin himself in a letter in 1871, have been resurrected as candidate sites for prebiotic chemistry. Shallow evaporative pools on continental margins where the concentration of dilute organics could periodically be boosted by evaporation. Impact craters with their cooling hot water at the margins have been proposed. Tidal zones, where the enormous Hadean tides repeatedly exposed and drowned large intertidal regions, have been proposed. Each of these environments has its own advantages and weaknesses as a proposed origin site. We do not yet know which of these, if any, is the right one. What is clear is that the Hadean Earth provided multiple environments in which prebiotic chemistry could operate for many hundreds of millions of years, under conditions that modern experiments have shown can produce at least some of the molecules that life requires. Did life actually originate in the Hadean? The question is difficult because direct fossil evidence of anything that old is almost non-existent. The rocks that could have preserved microbial fossils have, by and large, been destroyed. What evidence we have is chemical, isotopic, and textural, indirect proxies for the presence of biological activity read out of the very oldest rocks and minerals we can find. In 2015, a team led by Elizabeth Bell at the University of California, Los Angeles, working with Patrick Bainke, Mark Harrison, and Wenbo Mao, published a paper in the Proceedings of the National Academy of Sciences that startled the paleobiology community. They had been examining Jack Hill zircons under high-resolution imaging, looking for inclusions, small amounts of other material trapped inside the zircon crystals at the time of formation. Zircon inclusions are valuable because, being sealed inside the crystal, they can preserve original chemistry over billions of years. Bell's team found, inside one particular zircon crystal dated to 4.1 billion years ago, a microscopic graphite inclusion. And when they measured the carbon isotope composition of that graphite, the ratio of carbon-13 to carbon-12, they found a value strongly enriched in the lighter isotope, carbon-12. This matters because, on modern Earth and throughout the preserved geological record, biological processes preferentially use carbon-12 over carbon-13 when they fix carbon into organic compounds. The enzymes that catalyze carbon fixation, whether in photosynthesis or chemosynthesis or other forms of biological carbon acquisition, work slightly faster with the lighter isotope. As a result, biological carbon is typically depleted in carbon-13 relative to the source pool. Inorganic carbon, atmospheric CO2, dissolved carbonate in seawater, carbon from volcanic outgassing, tends to have a specific isotope ratio, and biological carbon is measurably lighter. The graphite inclusion found by Bell and colleagues had a carbon isotope value consistent with biological origin. If the interpretation is correct, this would be the oldest direct evidence of life on Earth, placing biological activity at 4.1 billion years ago, well within the Hadean, only about 300 million years after the moon-forming impact. It would mean that life emerged on Earth remarkably quickly once conditions permitted, and that the Hadean, contrary to its traditional reputation as a barren hell, was already biologically populated for most of its final 200 or 300 million years. The interpretation is, however, not universally accepted. Critics have pointed out several possible alternative origins for the isotopically light graphite. It could have come from abiotic processes involving certain types of hydrothermal chemistry, or it could have been introduced into the zircon after the zircon's formation, or the specific inclusion measured might not be representative. The case, as of the most recent reviews, is intriguing but not conclusive. Follow-up work on additional zircons and additional inclusions has continued, and the interpretation remains an active area of research. What the Bell result does confirm, at minimum, is that whatever the origin of the Hadean zircon graphite, the chemistry and the isotopic signature of biological-style carbon fixation were not impossible on Earth 4.1 billion years ago. Whether or not that particular graphite inclusion came from life, the Hadean was capable of supporting it, in the sense that its environmental conditions would have permitted the relevant biochemistry. Other lines of evidence from slightly later rocks are more robust. The Isua supracrustal belt of southwestern Greenland preserves sedimentary rocks approximately 3.7 to 3.8 billion years old, already Archean, but only about 300 million years after the end of the Hadean. These rocks contain graphite inclusions with the same light carbon isotope signature that typifies biological carbon in a geological context that is much easier to interpret than the single zircon case from the Hadean. Most researchers accept the Isua evidence as convincing confirmation of life by that date, which means that life was present on Earth by at least 3.7 billion years ago, within a few hundred million years of the end of the Hadean. And the timescale of chemical evolution to produce a living cell from prebiotic precursors probably requires at least some substantial period. So whether or not life began before the end of the Hadean, the trajectory was set, and some of the key chemistry that would make the earliest cells was likely already underway during the Hadean itself. All of this, the accretion, the magma ocean, the atmosphere, the oceans, the zircons, the pre-biotic chemistry, the possible first life, was happening on a planet whose sky was different from any sky that any human has ever seen. The Moon, immediately after its formation from the Theia impact, was much closer to Earth than it is today. How much closer depends on the specifics of the impact and the subsequent orbital evolution, but typical current estimates place the initial Earth-Moon distance at somewhere between 3 and 5 Earth radii, a tiny fraction of the modern distance of about 60 Earth radii. At that distance, the Moon would have appeared in the Hadean sky as an enormous object dominating the horizon, perhaps 10 to 15 times the angular diameter it has now, perhaps more. It would have filled a significant fraction of the sky. On the night side, it would have been a vast, bright disk, though exactly what the tidal heating of its surface at that early time would have looked like, visually, is an open question. Parts of its surface may have still glowed dimly from residual heat from its formation. The tides raised by such a close moon were enormous. On the modern Earth, the tidal bulge raised by the moon causes sea level variations of, at most, a few meters in open ocean and up to about 15 meters in certain unusual coastal configurations like the Bay of Fundy. The tidal force scales as the inverse cube of the Earth-Moon distance. At a distance of 5 Earth radii, the tidal force is 200 times what it is today. At 3 Earth radii, it is nearly 1,000 times. The early tides on the Hadean Earth were not meters, they were hundreds of meters, perhaps kilometers, at the most extreme. The Hadean shoreline moved by enormous distances with each tidal cycle, sweeping inland across the emerged landscape and retreating again, many hundreds of kilometers every tidal period. The tidal period itself was much shorter. Earth in the Hadean was spinning faster. Current reconstructions suggest a Hadean day was roughly 5 to 6 hours long, perhaps even shorter in the very early phase. The Moon's orbital period was also shorter, reflecting its closer distance. The result was a tidal cycle much faster than any modern tidal cycle, potentially several tides per Hadean day. The enormous tides swept the Hadean shoreline with a frequency that would have produced, in any tidal zone, intense cycles of heating, drying, re-wetting, and chemical concentration. Some origin of life models find these Hadean tidal cycles very useful. In cyclic wet-dry environments, prebiotic organic molecules can alternately dilute, concentrate, and polymerize with each cycle. The extreme tidal amplitude and frequency of the Hadean would have driven such cycling at a rate no modern environment can match. If prebiotic chemistry needs repeated concentration and dilution cycles to build up polymers, and there is good evidence it does, the Hadean tidal shoreline was one of the best environments in Earth's history for the task. The Moon has been retreating from Earth ever since the Theia impact. The tides it raises on Earth as it slows Earth's rotation transfer angular momentum from Earth's spin into the Moon's orbit. The moon moves outward by, on modern measurements, about 3.5 centimeters per year. In the Hadean, when the moon was much closer, the retreat rate was much faster, possibly tens of meters per year in the very early period. Most of the moon's outward migration happened within the first few 100 million years after its formation. By the end of the Hadean, the moon was still closer than today, but it was already well on its way toward its modern orbit. The day length has been lengthening correspondingly. Rotational energy lost to the tidal friction with the moon is slowing Earth's spin. The Hadean 5-hour day became, by the end of the Hadean, something closer to 10 or 12 hours. By the late Archean, perhaps 15 hours. By the Cambrian, about 21 hours. Today, 24 hours. The modern day is, on geological timescales, slightly longer than it was on a young Earth, and in the far future it will be longer still. The Hadean sky, then, was profoundly different from the modern sky. A sun perhaps 30% dimmer, but somewhat larger, and possibly a slightly different color as it settled onto the main sequence. A moon dozens of times larger in angular size, close enough that fine surface features would have been visible to a naked eye. A fast rotation that turned the entire sky across the horizon every few hours. An atmosphere, depending on the moment in the Hadean, that might have been orange-brown with CO2 and organic haze, or gray with thick cloud, or dim and red under a methane haze atmosphere. The particular visual appearance changed over hundreds of millions of years as the atmospheric composition evolved. If you could stand on the Hadean Earth, on a Hadean beach, looking out across a Hadean ocean at a Hadean sunset, the world you were in would be almost nothing like ours. Except, underneath everything, that the air was breathable chemistry, and the water was liquid water, and the ground was rock, and chemistry was already running, and the rocks under your feet were, in some of their finer chemistry, already setting up the conditions that life, eventually, would require. The end of the Hadean is, more than anything, a matter of stratigraphic convention. There is no single global event that marks the transition from Hadean to Archean at 4 billion years ago. The change is gradual. By 4 billion years, the impact flux had dropped enough that stable rocks could be preserved for long periods at the surface. By that same date, the Earth's mantle had cooled enough that tectonic processes resembling modern plate tectonics, subduction zones, spreading ridges, continental accretion, were beginning to operate in something close to their modern mode. The biosphere, if not yet established in the Hadean, was certainly well established by the early Archean, as the Isua rocks and their graphite isotopes confirm. The transition from Hadean to Archean is, in other words, a transition of degree rather than a transition of kind. The Archean, which will run from 4 billion years ago until about 2.5 billion years ago, will be the eon in which the Earth settles down. The biosphere diversifies. Cyanobacteria will, at some point during the Archean, invent oxygenic photosynthesis, though the oxygen will not yet begin to accumulate in the atmosphere. Continental crust will grow through repeated cycles of subduction and arc volcanism into the large, stable cratons that still form the cores of all modern continents. The moon will retreat further. The day will lengthen. The sun will continue slowly to brighten. By the end of the Archean, 2.5 billion years ago, Earth will look, atmospherically and geologically, quite different from its Hadean self, though still not yet like the modern world. The Hadean will be a layer far beneath the Archean surface, preserved in a few scattered Jack Hill zircons and in the general geochemical evolution of the mantle. The stones you can hold in your hand from any of these later eons will, at the deepest chemical level, still carry some signal of their Hadean origin. The isotope ratios, the trace element distributions, the subtle fingerprints that track the planet's long chemical evolution. But the direct record of the Hadean itself will be almost gone. It is worth, before the story closes, trying to hold the scale of the Hadean in mind. 600 million years. From 4.56 billion years ago, when the solar system formed, to 4 billion years ago, when the Hadean ended. 600 million years of a young planet, cooling and recovering from its violent birth, eventually hosting oceans, possibly hosting the first life, under a close moon and a faint sun, and an atmosphere no modern lung could breathe. 600 million years is, to put it in human terms, longer than the entire history of animal life on Earth. From the Cambrian explosion to today is about 540 million years. The Hadean is longer than that. If you took the entire duration of every species of trilobite, every dinosaur, every mammal, every fish, the whole fossil record of macroscopic animal life on Earth, and strung it together end to end, it would still be shorter than the Hadean, and we have almost no rock record of any of it. What we do have is the indirect record. Meteorites, whose chemistry is essentially unchanged since the solar system's formation. Moon rocks, whose cratering history constrains Earth's bombardment. Jack Hill's zircons, tiny and tough, preserving in their uranium decay chains and oxygen isotope ratios a handful of direct chemical measurements from the Hadean surface. Computational models that, given the physics we understand, reconstruct how magma oceans cooled, how atmospheres formed and evolved, how planetary rotation slowed under tidal friction. From this combination, fragments, analogies, models, isotopes, we have built a picture of what must have been the case during those 600 million years. It is not a complete picture. It is not a picture we will ever have in the detail with which we know the later eons, but it is enough to know, roughly, what the planet went through before it had any history it could record for itself. Everything that is familiar about Earth, the oceans, the atmosphere, the first life, the basic conditions under which any of the later story could happen, was set up in the Hadean. By the time the Archean began, 4 billion years ago, the planet had already done most of the hardest work. It had, in essence, become a planet capable of supporting a biosphere. The rest of Earth's history, the long, slow evolution from Archean microbes to the world we know, was built on top of a Hadean foundation. That foundation is still there, in the chemistry of the deep mantle, in the composition of the crust, in the isotope ratios of the oceans, in the tidal locking of the Earth-Moon system, in the very fact that we have a moon at all, which was not inevitable and which matters in many small ways for the habitability of the surface. The Hadean is the eon in which Earth became Earth. Before the Hadean, there was a solar system but no Earth to speak of. After the Hadean, the planet had a recognizable identity, and the story that would continue through every eon that followed could begin. And though we have almost no rocks from it, the Hadean is, in every way that matters for what the planet is now, still with us. The world we live on, the one that feels so solid and so old and so permanent, is the continuation of a Hadean beginning, a young, molten planet, a close moon, a faint sun, an ocean that condensed out of the atmosphere in a long rain. A chemistry that was, for hundreds of millions of years, getting ready to become life. And after all of that, only after all of that, did the rest of Earth's history, every single thing that would follow, begin. The world, which we often forget is old, was once very young. It had a night sky full of moon. It had a day that was too short. It had an atmosphere that would kill you. It had oceans that had just fallen from the sky. It was 600 million years of a planet becoming itself before anything like the planet we know was here. That was the Hadean.